how can we handle exceptional situations in a program? Things like division by zero, or opening a file that does not exist, or square root of a negative number. Things that are errors inside the program, but also things that might happen from outside. Maybe someone removes a file while the program is reading it. So these things happen rarely, but we have to take care of them. So in order to do that, we will add a new programming concept called exceptions. So we'll define exceptions and show how they're used, and we'll give the semantics of exceptions in the abstract machine. So the thing is, with exceptions, we'll be able to handle these exceptional situations without cluttering up the program with error-checking code that is extremely rarely used. So the program will be able to focus on the case when there's no error, so it will remain readable. So the principle that makes it work is called the containment principle. So when there's an error, we want to recover from this error, and we would like the error to affect as little as possible of the program. So we want the program to go on and not to restart the whole thing. So in order to do that, let's propose a principle, the containment principle. So we say a program is a set of nested execution contexts, starting from small going to bigger. They're kind of like dams, and when there's an overflow or a flood in one level, the next level will catch the flood and keep it from spreading. So an error will occur inside one execution context, and there's a recovery routine, exception handler, which exists at the boundary. So at the level exactly where the dam is, and it does its best to make sure the error does not propagate to the next higher execution context. So it sort of works like this. So here, the ovals here are execution contexts. So there's netted ones. The red oval is one with where there's an exception handler, and the little X here is where there's an error. So the program is executing here somewhere, and at some point there's an error. And when there's an error, we make an operation called raising an exception. This triggers the exception handling mechanism, and we will jump to the nearest and closing execution context. And here, these three contexts have no handlers, so we will jump to the fourth one, which does have an exception handler. And it will get a reference to some information telling us what the error is, and it will recover. It will do something to fix the error. Okay, so that's the idea. So to make that work, we add two new instructions as interface to this exception handling mechanism. A try instruction, which will create one of these ovals, will create an execution context, and a raise, which when executed inside of an oval will jump to the nearest and closing oval. Okay, so it works as follows. Let me first explain it briefly, and then I'll show with a figure, and then I'll give an example. So the try instruction puts a marker on the stack. So the execution context is related to the semantic stack. So the try puts a marker there, and then it starts executing the body, S1. So you have the marker and you're executing. If there's no error, then this instruction will terminate normally, and the marker will be removed, and nothing special happens. Okay, that's the most common case. Now, if during the execution of S1 there is an error, then we will execute the raise. What the raise will do, it will empty the stack, look for the marker until it reaches the marker. So this cancels the rest of the execution of S1. It will then remove the marker, put S2, which is the recovery code, on the stack, and the variable y, which is in the catch clause, will refer to the same variable as x. Sorry, the identifier y will refer to the same variable as x. So that means information is passed between the raise and the catch. So in a picture, it goes like this. So here on the left, we have our execution up to the point when we start the try. Now we will create the execution context with the try. So we put the marker and we start executing S1. Now there's two possibilities. Either there's no error, this is the top arrow, then S1 will eventually terminate, we will reach the marker, and then the marker is removed and it's done. Nothing special happens. The second possibility is if there's an error, so a raise, the raise will empty the stack, remove whatever's left of the S1 execution, reach the mark, remove the mark, and put S2, which is the recovery code. And then execution continues with recovery. So to make it more clear in terms of a picture, what are the contexts and how they relate to these instructions? Here are 3 nested try instructions. So I'm coming down here, I execute the first try instruction. This will put in the first mark here. 1, 1. Execution continues. Eventually I reach the second try instruction. This will put a second mark here. And execution continues. Eventually I reach the third try instruction, and that will put a third mark. That means there are now 3 execution next contexts that are nested. Context 3, 2, and 1. Now eventually context 3 finishes, it's removed, so this will then remove this part. Context 2 eventually finishes and removes, and context 1 eventually finishes and removes. So everything goes away, unless there's an error, and in that case, one of these recovery instructions will execute instead.